One. All right, so fast review. All right, so the tightrope walkers use these sticks. So what's the purpose of this stick?
Cool. It's ready. I'm ready.
So pilots inside a centrifuge. This guy is going to be taken up to about 8 or 9 Gs within a few seconds. 9 Gs, perfect. Notice that there was a rotational acceleration involved, aside from the centripetal acceleration. So when you have two different types of accelerations, how do you find the total acceleration? Geller's incline experiment. The premise of the experiment is to slow the motion down because it was trying to figure out the acceleration due to gravity. But for it to work, objects rolling down should be rolling at the same acceleration, right? Would they be accelerating at the same rate? Falling chimney is going to break at some point, somewhere in the middle. So the question is why? So those are the typical test questions that I would have for the conceptual portion of the test. Basic terminology. This is for the multiple choice section of the test. Angular displacement is the angle. It's going to be expressed in terms of radians. 1 revolution or rotation is going to be 2 pi radians. It's going to be 360 degrees. Angular velocity is how fast the angular displacement changes in time. So angular displacement goes from an initial value to a final value within this time period. So which means that it's going to have a rotational velocity. It's going to be expressed in terms of radians per second. We'll have angular acceleration, which is how fast the angular velocity changes in time. Here's your initial angular velocity, which is this. Final angular velocity right there. So this is how fast the angular velocity changes in time is your angular acceleration. It's going to be expressed in terms of radians per second squared. Angular variables can be expressed in terms of their tangential variables. Tangential variables are the variables along the direction of the curvature that you got. You got this length of the curvature, which is known as the arc length. If you know the angle, if you know the radial distance, you can figure out the arc length from that. You can figure out the speed along the direction of the curve. That's known as tangential velocity. So if you know the angular speed multiplied by the radial distance, it's going to give you the tangential velocity. If you know the angular acceleration, you can figure out the tangential acceleration by multiplying everything with the radial distance to that point. So the angular terms are on the right-hand side, and then linear terms will be on the left-hand side. So angular terms will, as long as you multiply the angular terms with the radial distance, you will get the tangential linear terms. All right, if something is moving in a circle, which means it's got speed, it's going to have tangential speed. Anything that has tangential speed is also going to have centripetal acceleration. All right, so this is from earlier chapter. So square of the speed divided by the radius is going to give you the centripetal acceleration. Tangential speed can be expressed in terms of the rotational speed. In doing so, we will come up with a second formula for the centripetal acceleration. All right, so this is for the multiple choice sections of the test. Either this or that formula will become useful. All right, so if this thing is also tangentially accelerating, if there's a tangential acceleration, there's also, in addition to the centripetal acceleration, in addition to tangential acceleration, it's going to have centripetal acceleration. So which means that we have to look for the total acceleration. The way to do it is you got two vectors, form a simple right angle triangle. Now look for the hypotenuse. All right, so square of the base plus the square of the height is going to give you the square of the hypotenuse. And then you can figure out the angle if you know the base and the height using either the tangent of the angle, sine or cosine of the angle. Traditionally, we use the tangent. Well, if the acceleration is constant, the motion becomes predictable. These are our linear kinematics equations. All right, so if you know the time, you know the location. You know the time, you know the speed at that time. You know the location, you know the speed at that location. We'll do the same thing by transforming linear terms into the angular terms. And we will have 3 rotational motion equations, so rotational kinematics. If the acceleration is constant, once again, you can figure out the final angular displacement, final angular speed at this time as well as at this angular displacement location. Okay, so rotational motion. All right, so displacement is the shortest distance between 2 points. As the final location is indicated as an arrow. Rotational displacement is the angular displacement, expressed in terms of radians. Average speed is measured distance over measured time. Rotational speed is the measured rotational displacement over time. Rotational speed is going to be expressed in terms of radians per second. The average acceleration is how fast the measured velocity changes in time. Average rotational acceleration is how fast the rotational velocity changes in time. Arc length is the length of a curvature. You can figure out the arc length if you know the rotational displacement. And then the only thing you have to do is multiply the rotational displacement with the radial distance where you want to measure the arc length. Tangential speed is the speed along the direction of the curvature, along the direction of the curve. If you know the rotational speed, you can figure out the tangential speed at any radial distance you like. Speedometers are they're configured to measure the rotational speed of the car. And the actual speed of the car depends on the radius of the tires, because you take this rotational speed and multiply it with the radius of the tire, right? So if you have large wheels, the car is going to be moving faster than what's on the speedometer. Tangential acceleration is the acceleration on the direction of curvature. All right, so if you know the rotational acceleration, you can figure out the tangential acceleration at any radial distance by multiplying the rotational acceleration by r. If an object has both centripetal and rotational accelerations, all right, so you do a vector addition of these accelerations, you make a small triangle and find the hypotenuse of that triangle. What makes linear motion predictable is constant acceleration. Likewise, the rotational motion will become predictable when the rotational acceleration is constant. Inertia is the tendency to retain motion or resistance to change in motion. Motion means velocity. So inertia is caused by mass. Moment of inertia is the rotational mass-like expression. So we'll get back to that. All right, so it's the rotational inertia. Potential energy is the stored energy. Depends on height, or if it's a spring mass system, depends on the compression or stretching. The amount of stretch that the string undergoes. Spring undergoes. Kinetic energy is the energy of motion related to the square of the speed for a given mass. Mechanical energy is a combination of kinetic and potential energies. Conservation of mechanical energy is the constancy of mechanical energy. And that's it from. All right, the only thing I'm interested in from this section is the expression of mr squared. So we got the torque, that's the rotational force. We got a rotational mass-like term, and we got the rotational acceleration. So this rotational mass-like term is known as moment of inertia, or the rotational inertia. They mean the same thing. This one is a generic expression for the moment of inertia. All right, so it's going to be mass times the square of the radial distance to the point of rotation. All right, so one of the things that we need to focus on is if you have multiple masses, you need to sum up the moments of inertia relative to the point of rotation. All right, in case there are questions like that in the multiple choice section. All right, so moment of inertia is going to depend on the geometry. Different geometries will offer different amounts of moments of inertia. All right, so moment of inertia is the tendency to retain rotational motion or resistance to change in rotational motion. All right, so the important shapes to remember is the first one, A, hoop, mr squared. Solid cylinder, it's going to be 1/2 of this one. Uniform sphere, it's going to be 2/5 mr squared. Long uniform rod held in the middle, in this case, the point of rotational axis is in the middle. It's going to be 1/2 m L squared. L is the length of the rod. Or when you move the point of rotation to the bottom or one of the edges, this becomes 1/3 ml squared. So these are the standard ones that we would use. In terms of the tightrope walkers, long uniform rod, notice it offers tremendous amount of moment of inertia. So how much moment of inertia, rotational inertia, resistance to rotational motion it offers depends on the mass. These things tend to be fairly massive. And also depends on the length. They make it as long as possible. All right, so that when you're about to lose your balance, you can just lean into it. And it's going to offer tremendous amount of resistance to change in rotational motion. As a result, you're going to be able to balance yourself better. All right, so that's the answer to that question. So we answered at least one of the conceptual questions so far. All right, so this is the speed along the direction of the curvature. So that's your tangential speed. Tangential speed can be expressed in terms of the rotational speed. In doing so, we end up getting a rotational mass-like term. So that's your rotational inertia multiplied by the square of the speed, rotational speed. This rotational speed is the speed relative to the rotational axis, which usually is the center of mass for rotating massive objects that you're looking at. And this is, I mean, if it's a soccer ball or a bicycle wheel or whatever, this represents the tangential speed, the speed at the rim that you're looking at the boundary. So this is the speed relative to the center of mass in terms of the rotational speed. Let's just go back up and says that. All right. So here's your rotational speed. Now, objects will have two kinds of rotating objects will have two kinds of kinetic energies: rotational kinetic energy due to the motion relative to the center of mass, and they will also have the translational kinetic energy, which is due to the motion of the center of mass. Center of mass is going to have a kinetic energy, and the rotational motion is going to have a kinetic energy relative to the center of mass, expressed relative to the center of mass. So combination is going to give you the total kinetic energy of a system. All right, so total kinetic energy of a system, it's best illustrated using this problem. Obviously, bowling ball problem is a good one, because normally if you're following the center of mass expression is going to be 1/2 mv squared, but also the bowling ball is moving relative to the center of mass, or in this case, this axis of rotation. So it's also going to have a second type of kinetic energy, which is the rotational kinetic energy. So what you need to do is you have to kind of combine both of them. And then the math works out in such a way that the total kinetic energy is going to be more than 1/2 mv squared. I'm going to focus on this problem briefly. There are two reasons for it. We're using the conservation of energy for this one. One reason is I want you to notice something mathematically, and there's something conceptual that we will discuss out of it. So tip is the one that we're following. How fast is the tip falling? What's the speed of the tip at the moment of impact? There we go. All right, so this motion is going to be happening under the influence of gravity and gravity only. So as a result, the mechanical energy is constant. The only thing which is interesting here is the initial setup. The rest of it is math. Not the mathematical details, but the initial setup of this one. Initial mechanical energy at this point is going to be all potential. And the final mechanical energy is going to be all kinetic, but it's going to be all rotational kinetic. All right, so because we're measuring everything relative to the point of rotation is here, so the point of rotation does not have any linear kinetic energy. It doesn't have any tangential. It doesn't have any. It's like the center of mass. Center of mass is actually here, but this is like the point of rotation. Rotational axis is here. Rotational axis is not moving, so which means it doesn't have any. Rotational axis does not have any kinetic energy. This point has rotational kinetic energy. That's the reason why this is the formula that we end up using. All right, so how you pick this formula requires understanding, in essence. All right, so I say, okay, so motion is happening. The motion is being pivoted with respect to this point. And so this is the rotational motion relative to your rotational axis. Rotational axis is located here. So rotational axis does not have any translational kinetic energy. So hence the reason why everything is rotational here for this problem to work out. And then when we took this problem one step further, it turned into a mind twister, because the top of the pole, the tip of it, according to a computer scientist that I was talking to from MIT, was supposed to move faster than a falling object. And at first, I mean, I went, okay, that's not true. He didn't know exactly how this was supposed to be done, but he remembered well enough that his professor actually did this derivation on the board. And that's the only motivation that I needed, that there was something here. So I decided to do it myself. So in free fall, this is the speed of the falling object at the moment of impact. In rotational motion, based on the previous solution that I had, I was able to figure out the speed of the tip of this pole, came up with a mathematical expression for that one, which happens to be the best. Only to realize that it was right, which means that this rotating object would be hitting the ground at a larger speed. It's the speed of the tip is almost 1.7 times larger than the speed of the falling ball, which means that the tip accelerates more rapidly than the freely falling object. So the question is not why, because it's an easy thing to explain. Because of the rotational motion itself, which I'm not interested in. What's interesting is this explains why the falling chimneys break at some point. The reason why they break, and this is once again a good test question, is under the influence of gravity, acceleration is going to be 1g. All right, so all the way up to the center of mass, everything is going to accelerate at 1g. Right, so center of mass accelerates at 1g usually, and every single point up to that point is going to accelerate at a rate which is going to equal to 1g. Anything above that point is going to accelerate at a rate which is larger than 1g. All right, so now for you to be able to accelerate things at a rate larger than the gravitational acceleration, you have to pull them down. All right, you have to pull them down in this direction. Now, for you to be able to pull them down in that direction at a rate larger than the gravitational acceleration, the structure needs to be properly reinforced in the lateral direction. All right, these chimneys are not properly reinforced in the lateral direction for that purpose. They're reinforced just enough so that if there are winds or whatever, you know, they're going to be in one piece. But this requires tremendous amount of tension on the structure in order to keep the structure together. And this structure is not properly reinforced laterally to be pulled down at a rate larger than the gravitational acceleration. That's the reason why they usually break apart. All right, so they will break at or around the center of mass usually of that structure, because everything up to that point is going to fall under the influence of gravity at a rate which is 1g. Anything above that has to be forced to move at a rate larger than 1g. All right, so we covered two of the observations, basic observations. This is one of my favorites. So this is a car on black ice. You lock up the brakes, and then guess what? The car speeds up. Okay, so it's counterintuitive. So how's that possible? Can a car speed up on a perfectly frictionless surface? The answer to that question is, it so happens, yes. And the only way you can explain it if you have a really good understanding of the concept. Let's pretend that the ice offers no friction. It's perfectly slippery. So which means that no work is being done on the car because there's no external force acting on the car. The car is getting displaced, but there's no force acting on it, which means that there's not going to be any change in kinetic energy. So kinetic energy of the car is not going to change. But kinetic energy is the total kinetic energy of the car is not going to change. The total kinetic energy has two parts. One of them is the translational kinetic energy of the car. So that's how fast the center of mass of the car is moving. The second comes from the rotational kinetic energy of the tires. So it's the total kinetic energy of the car is the combination of these. So if you lock up the brakes, you're reducing the rotational kinetic energy. And kinetic energy cannot be destroyed or created. Energy cannot be destroyed or created, obviously, under the circumstances, because there's no friction acting on the car. But it can get converted into the translational kinetic energy, which means that the center of mass of the car is going to end up moving faster. So the rotational kinetic energy gets converted into the translational kinetic energy of the car. All right, so we did explain 3 out of 5 main observations so far. So moving forward, Geller's incline experiment. All objects fall at the same rate. Does this mean that they will roll at the same rate? All right, so we'll do a generic derivation. Your test question is going to be related to this. This is one of the questions that I would focus on getting ready for the test. Whether you're a college physics student or university physics student, it doesn't matter. This is one of the problems that I want you guys to focus on. It's a generic problem. All right, so it's a generic problem. It's got some conclusions that we will use in the conceptual as well as the multiple choice sections of the test. So we've got a solid and a hollow cylinder. So which one is going to reach the ground sooner? Initial height is given. Ignoring friction, gravity is known for sacking. Mechanical energy is conserved or constant. Initial and the final components of the mechanical energy. Kinetic energy is a combination of translational and rotational. Potential energy is related to height. All right, so the final total mechanical energy. Initial total mechanical energy. It looks nasty, but it's not. We got zeros. Final height is going to be 0. Initial speeds, tangential, the translational as well as the rotational will be 0. All right, so from here we'll come up with an expression for V. So isolate V. Before isolating V, I just want to express the rotational speed in terms of the linear speed. I'll do it by substitution. All right, so 1/2 V squared will be pulled out. All right, so divide both sides by the expression in the parentheses. All right, so we'll stop at this point, just briefly. All right, so general expression that we got here. Speed and moment of inertia will be inversely proportional. right, so the larger the moment of inertia is, the slower the speed is going to be. So how fast something is going to roll depends on the moment of inertia. Larger the moment of inertia is, the larger the resistance to change in rotational motion is, the slower it's going to move. All right, so and then we've got the hollow cylinder, mr squared. Let the math take care of itself. All right, so when you put in the expression for the moment of inertia, notice that the mass and the radius will not matter in terms of final speed. Only thing that matters is the initial height. All right, when you're looking at the solid cylinder, number diagram is slightly different. Once again, the mass is not going to matter. The size is not going to matter. The only thing that matters is the shape, as it so happens. All right, so the solid cylinder is going to have a larger speed because it's got a moment of inertia, which is half the moment of inertia of the hollow cylinder. All right, so the question is, out of this one, moment of inertia of the solid is going to be half of that of the hollow cylinder that you got. Hoop is going to be mr squared. The solid is going to be 1/2 mr squared. Why? Imagine that they have the same mass. All right, so you got the mass here, you got the mass here, and both of them are the same mass. Solid cylinder is still going to have a moment of inertia, which is going to be half of the thin hoop that we got. So the question is why? Again, all right. So this is the sort of question you're going to be required to be able to answer on the test. Okay, so that requires an understanding. Here, all the mass is located at this radial distance, away from the axis of rotation. Here, all this mass is uniformly distributed into the volume away from the axis of rotation. If you can concentrate all your mass at this radial distance, that's going to increase your moment of inertia. If the mass is uniformly distributed, that's going to reduce your moment of inertia. All right, that's the reason why. All right, so that's the reason why. It doesn't explain why it's 1/2, but it explains why it's going to be smaller. The moment of inertia here is going to be smaller than here, because the moment of inertia of each and every single mass, the portion of mass that you're looking at is going to be related to the square of the radial distance away from the rotational axis. So the contribution of the mass near the rotational axis is going to be smaller to moment of inertia, and the contribution of the mass away from it is going to be bigger. So you just have to add up all those contributions, and when you do that, it's going to give you a moment of inertia which is going to be smaller than the moment of inertia if all the mass were to be located at the same radial distance away from the point of rotation.
Every Winter Olympics, the figure skating competition is a big draw, all the more.
So, what is the trick of being able to do a quad? What's the difference between a double axle, triple axle versus a quad? Is one of the questions that we will have to deal with. Earthquake 2011 shrunk the radius of the Earth by about 7 inches. As a result, the Earth sped up, gained rotational speed, and it shortened the days by, 1.8 microseconds. This is what happens. Question becomes, how does the Earth speed up in the absence of an external force acting on it? So how do you accelerate in the absence of an external force? This car starts to turn the wrong way, and the reason why that happens is because this guy applied the brakes. Why would applying the brakes while you're airborne influences the rotational motion of the car? Squirrel, as it's trying to get closer to the bird feeder, speeds up, starts to accelerate. There's a rotational acceleration as the squirrel starts to get closer to the bird feeder. But how do you generate acceleration in the absence of an external force like the torque?
Having now, for the first time,
Kepler's second law, according to which planets, when they get closer to the sun, they will speed up. Away from the sun, they will slow down. Once again, this is happening in the absence of an external force acting on the system, the solar system. So what causes acceleration in the absence of an external force? These are always the same questions. Lastly, the falling cat. How does a falling cat ride itself up in midair? So rotates just enough and then stops rotation in as soon as it's. All right, so we got the concept of torque. A couple of things to emphasize here is the torque is a rotational force. The component of the force which is responsible for torque is going to be 90 degrees to the radial arm or lever arm. And then you will have to find that depending upon the geometry. All right, so you'll have to find the component of the force which is 90 degrees to the radial arm that you got. All right, in this case, it's F time. It's going to be sine of the angle of theta that we got. So we do a back substitution. So this is the generic formula. Whether it's sine or cosine is going to depend on the geometry. That's what I'm getting at. Counterclockwise twist is going to be positive. Clockwise twist is going to be negative. All right, so if you're looking for the net torque, I'm not going to go into the details of this. I'm just going to look at the way this is done. All right, so this force is trying to cause a clockwise twist, so this is going to give you a negative torque. This force is trying to do a counterclockwise twist, so this is going to give you a positive torque. This force is trying to do a clockwise twist, so this is going to give you a negative torque. All right, so that's how you do your torque additions. Angular momentum is going to be conserved in the absence of a net external torque acting on a system, so it's going to remain constant. In the case of the swirl, if you're trying to bring the mass near the point of rotation, the tangential speed is going to go up because L is constant. That's what it means. If you move the mass away from this point of rotation, this tangential speed is going to go down. So you got that relationship. In the case of the Earth, all right, let's go back. When you shrink the radius, when R goes down, it's going to reduce the moment of inertia of the Earth. As a result, the rotational speed is going to go up. So that's what happened to the Earth. Radius shrunk, rotational speed went up, and the days got shortened slightly. Figure skaters, the only thing that they have to do is pull their arms in order to increase their rotational speeds as they're rotating. All right, so because the angular momentum is conserved, it's going to be constant. By pulling the arms and legs in, they're able to reduce their moments of inertia. As a result, their angular velocities will go up. Angular momentum of this car is conserved, cars and the wheels. If you lock up the wheels, the rotational motion is going to get transferred to the car. And so that's what's happening. So the car starts to rotate. All right, so force is what causes acceleration. Torque is a rotational force. Acting on a rotational mass-like term is going to cause a rotational acceleration. This is a generic setup for a torque equation. So you got a force applied to this point at a given angle relative to the radial axis. So the only thing you have to worry about is the component of the force which is tangential. The component of the force which is perpendicular to the radial arm. Counterclockwise twist is positive torque, clockwise negative torque. Work is a combination of force and displacement. Rotational work is a combination of torque and rotational displacement. Momentum is mass moving at this velocity at a given velocity. Angular momentum is the rotational momentum. Rotational mass-like term spinning at this rate that can only also be expressed in terms of the tangential velocity. Absence of an external force is what conserves momentum. Absence of an external force on a system is what conserves momentum. Absence of an external torque on a system is what conserves angular momentum. If the moment of inertia is suddenly reduced, if I goes down, omega is going to go up, angular velocity is going to go up. What happens to angular momentum if this moment of inertia is suddenly reduced? Nothing is going to happen to angular momentum. It remains constant. If you suddenly increase the moment of inertia, the angular velocity is going to go down. Rotational kinetic energy is going to go up when the moment of inertia is suddenly reduced. The extra energy is going to come from your muscles, which means that the kinetic energy is going to get converted into, the chemical energy is going to get converted into kinetic energy. Conditions for equilibrium, net force is going to be 0. The net torque is going to be 0.
Hey, it's me, Destin. Welcome back to Smarter.
All right, the way the cats write themselves up. This is a really good physics problem. I mean, it took a while to figure this out. the cat creates two rotational axes relative to the center of mass. So there's going to be a rotation relative to this axis, and there's going to be a rotation relative to the second axis. How fast the rotation takes place is going to depend on the moment of inertia. All right. So by extending the legs, you can increase the moment of inertia. In doing so, you're going to reduce the angular velocity because there's no external force acting on this cat. There's no external rotational force acting on this cat. So angular momentum is going to be constant. So you can stretch the legs up during the rotation. So the back end is not going to spin as fast as you're pulling the legs in from the front end. So the front portion is going to spin faster relative to the axis of rotation. So by adjusting the moment of inertia, making it bigger, the speed is going to go down. And making it smaller, the speed is going to go up. The cat makes the adjustment just so it's able to do a full turn.
This video.
All right, so chapter second one is the one that I'm interested in. All right, so here's a solar system. There's no net external torque acting on the system, so angular momentum is conserved. When the angular momentum is conserved, the speed depends on the radial distance, tangential speed. Further away, notice that the planet slows down. Nearby, it's simply going to speed up. This is the conservation of angular momentum.
If a body remains stationary in its position, we
All right, so equilibrium.
say that it is in equilibrium.
All right, so three types of equilibrium. One of them is the neutral equilibrium. When it's neutral, center mass remains at the same distance relative to the point of contact. When you displace the system from its equilibrium position, that distance remains the same. That's a stable equilibrium. Unstable equilibrium, this one is in equilibrium, but if you displace it from its equilibrium position, center mass is going to end up losing potential energy. All right, so in the neutral one, potential energy is constant. Unstable, the potential energy goes down. And when it is stable, when you displace it from its equilibrium position, all right, so potential energy goes up and then goes back down again to its original. All right, so that's stable equilibrium. Okay, we got two conditions for equilibrium. The net force is going to be 0 along the x, y, and z axes. And then the net torque is going to be 0. So the system is not going to rotation. Okay, so I'm not going to do this problem. This problem was done before early on. We didn't do it in classes. Go to the lecture links and just find it if you don't know how to do it. These are standard physics problems, so make sure that you know how to do these problems when you're studying for the test, especially for the multiple choice section of the test. All right, it's straightforward. I don't think so. I'm going to kind of skip over that one. All right, this problem is a problem that I'm going to recommend for college physics students in general and for university physics students. Once again, you may get a few questions like this on the multiple choice section of the test. I'm not going to focus on the details of this. The only thing I'm going to focus on is the setup. That's the most important thing regarding this. All right, so you got a diving board. There's a person standing on it. All right, and this person has weight. This weight is going to create all sorts of reaction forces on the system. The board is resting right at this point, so there's going to be a support force here. But that's the normal force, and it's rigidly attached to point A, so there's going to be a support force pointing in the downward direction. So whatever this is, this one is going to experience tension. This is going to experience a normal force. And the tension and the normal force is created by the weight of this person. So these are both of them reaction forces. All right, so I'm also, when I'm setting it up, I noticed that numbers are given. So this is my lever arm. The first one, this is the second one, whatever. So I'll use L for that, the length is the proper way of doing it. All right, so I'm going to just ignore the numbers just for now. All right, so we got two unknowns in this case. If you have two unknowns, you will need to have two equations to solve for two unknowns. So which means that you need to generate two equations. The way to do it is it's an equilibrium problem. So you can just sum up the forces all in the y direction. And there's not going to be an acceleration on the y direction. So that's going to become our first equation. And then you can sum up the torques relative to a pivot of your choosing. All right, so the next one that we're interested in. I decided to put my pivot right here. I could have put it right there. So it doesn't matter. So you can put it here or you can put it there. And then the rest of it is, obviously, this is trying to cause a counterclockwise twist. So this is going to be a positive torque. This is trying to cause a clockwise twist. So that's going to be a negative torque. All right, so F1 is trying to do, all right. All right, so, and then, just sum up your torques, the net torque is going to be 0, and then the rest is going to skip that. For university physics students, 11 is what I like. All right, so this is the sort of stuff that you will need for your engineering classes. Oh, let me just go back to this one. For college physics students, I want you to do problem number 10. And in this problem, it was assumed that this was weightless. If I were to give you a problem, the platform would also have weight. So just place the weight of the platform in the middle somewhere. All right, so it should be at the center of it. All right, so that's gonna become fairly obvious in this problem. All right, so this is an overly simplified version of a ladder problem. It's a classic problem. It's got weight. The weight is going to be applied to the center mass. And then you need to identify each and every single force acting on the system. It's resting against the wall, so the wall is exerting some kind of reaction force. This would be the normal force, but I'm going to call it the push. The ground is applying 2 forces. One of them is in the horizontal direction, that's going to be friction. The other one is in the vertical direction, that's the normal force. All right, so the whole idea is to figure out these reaction forces, like G's as well as P's or whatever. So P is the push from the wall. All right, so the ladder is leaning against the smooth wall, which means that the frictional force along the opposite direction is actually ignored in this case. All right, so the length of the ladder is given. The weight is given. We got 3 unknowns in this case. Angle is given. So if you have 3 unknowns, you need to have 3 equations to solve for 3 unknowns. You can easily generate 3 equations out of this. You can sum up the forces on the x direction, along the y direction, and then pick a pivot and then sum up the torques relative to that pivot. So the net torque is going to be 0, the net force is going to be 0. All right, so that's more than enough to come up with 3 equations. Oof. All right, so once again, the only interesting thing about this problem, not the details, but the setup. All right, so sum up the net force on the x direction, sum up the net force on the y direction, and then sum up the net torque relative to a pivot of your choosing. I usually pick my pivot right here. Okay, so if your pivot is right here, you don't have to worry about these 2 forces, those 2 unknowns. All right. So I'll pivot everything right to that point. All right, so how this is done is important, because this angle is the angle that you will need to use in order to analyze P as well as W in this case. All right, so the component of W, which is going to be responsible for torque, is going to be the component of W, which is going to be perpendicular to this radial distance. And so for you to be able to calculate that, you need to know how this theta figures into this geometry over here. So this angle becomes the angle right here. All right, so you have to make a similar triangle, only to realize that this angle happens to be this angle here. So component of the weight, which is 90 degrees to the radial arm, is going to be, this is adjacent over the hypotenuse, so that's going to be cosine of the angle of W. All right, now to get this force, and once again, you're going to be interested in the component of this force, which is going to be perpendicular to the radial arm. So the component of this force, which is 90 degrees to the radial arm, is going to be in this direction. And then I'm going to make a small triangle by moving it here. And this angle is the same as that angle now. All right, so I placed the angle here. So this is the component of this force, which is 90 degrees to the radial arm. And this time it's opposite over the hypotenuse, so this is going to be sine of the angle of P. And the rest is, it's a torque equation. So we just. Okay, so rollover speed. I didn't give you a problem like this, obviously. That was more of a discussion thing. This is a 3-dimensional system calculation, something that you guys will learn how to do quite well in engineering statics. So you'll be doing this stuff day in and day out. You don't have a choice. Everything that we discussed, these are the basic concepts. And everything that we've been doing 2-dimensional, you will get to do in 3-dimensional setups. All right, so rollover speed, this is the maximum speed at which you can negotiate a curve without rolling over. All right, so when you reach this maximum speed, the vehicle is going to balance itself on 2 of the lateral wheels on two side wheels. That's what happens. So it depends on the radius of the curvature. The bigger the radius of curvature is, the faster you can actually negotiate that curve without rolling over. It depends on the separation distance between the tires. Okay, so the wider the vehicles are, more balanced they will be. So which means that they can actually negotiate these curves at much higher speeds. Also depends on H. H is this location of the center of mass. Higher up the center of mass is the slower the speed at which the rollover is going to happen. All right, so we talked about school buses. They got high center of gravities. Higher the center of gravity is, obviously more prone they become to rollovers, but they're being overly cautious usually. These vehicles are designed to negotiate these ramps at or near the actual maximum speed that these ramps are designed for. All right, so the ramps are designed for like 60, 65 to 70 miles per hour. These vehicles are not going to roll over as easily. It's just better on math.